Welcome to the lecture Digital 3D Documentations in Archaeology. In this lecture part, we want to talk about automated flight planning for aerial documentation campaigns. Here we see an overview of the topics we want to discuss in this lecture. This should help us later to find the individual topics more quickly. Let's start with the somewhat provocative question. Can 3D documentation always be completely automated? With the knowledge gained from the last lectures and the experience gained with manual flights and the associated recording strategies, it is now also possible to carry out automated or at least partially automated flight campaigns. In practice, in addition to large areas that can be flown automatically, we will often have to reach for the controller or even a camera ourselves. So we can answer the first question with no. In an archaeological context, automated surveys can cover much of the area, but often must be supplemented by manual surveys. However, a lot of time and work can be saved by an automatic flight. A number of different free and commercial programs are available for automatic flight planning. A research on the available and compatible software systems is worthwhile and should be repeated from time to time. A very easy to use software we want to start with is called PrecisionFlight. A good entry-level variant with a compact operation is offered by the program PrecisionFlight, which can be installed on a smartphone or a tablet. Unfortunately, missions cannot be planned offline. Everything has to be done on the field. We can mark a polygon within a map and specify a flight altitude. The flight planning in terms of starting point and destination, as well as the trajectories, adjust automatically. After the flight planning, the flight can be executed directly. In this example, an area of 4.9 hectares was flown over at an altitude of 50 meters on Iceland. This required 9 minutes of flight time and 176 individual images were captured. PrecisionFlight calculates 1 centimeter per pixel for the image resolution of the orthophoto. When calculating with the web service Drone Deploy, 1.6 centimeter per pixel could be achieved in the orthophoto. But which software packages are available and according to which criteria should we select them? The available software packages should be evaluated according to criteria relevant to the documentation campaign. Does the software support the existing device? Can offline maps be downloaded or imported? Can the missions be planned offline before the campaign? What is the software's manageability and reliability? How and which flight and recording parameters can be set? Can several missions be planned offline in parallel, so-called multi-missions? Does the software provide an estimate of battery requirements and flight time for a mission? What is the maximum flight altitude possible with the software? Can the takeoff and landing points of a mission be changed individually? Does the software estimate the resulting ground resolution of the result? Here, it must be decided in advance which of the criteria are decisive for the documentation campaign. The speed of development in this area is enormous and a number of very good free-to-use solutions are available. After an extensive evaluation in 2018 of all freely available programs for the documentation campaign in Mongolia, where nearly 50 square kilometers were to be imaged in less than a week, the Pix4D capture program was selected as the preferred one. The campaign was very successful and will be presented in detail later. The two most important criteria for the deployment were an offline planning of multiple flights within an area and the free setting of the flight altitude. On the smartphone or tablet that will later be used for communication with the DJI Phantom 4, the current version of Pix4D capture must first be installed. After the start, one of the supported devices is selected, and thus the pairing to the multicopter is made. Now a project can be created. Here it is important to note that a project can combine and manage multiple flight missions. This also means that the performance of the tablet can decrease significantly when flying if there are too many missions in a project. A meaningful, comprehensible and clear project naming is self-evident. By the way, the projects can be copied and thus transferred to other devices. After a documentation campaign, it is also advisable to back up the flight data. In this way, questions such as flight altitude, camera orientation, or recording strategy can be answered. Copying the project data into Pix4D capture is also suitable for the monitoring aspect. This means that a specific shot can be taken repeatedly at one location with the same camera and flight settings. In this way, comparable models can be created, which can later be registered and compared in Cloud Compare, for example. An example shows a documentation process underwater. For flight planning, polygons can be created in Google Earth, for example, to delimit an aerial flight area. The polygon can be colored and can be used as a basis for documentation later. After the flight area has been prepared, it can be exported in KML format. KML is an XML-based data format developed by Google for storing geographic data and can be used directly in Pix4D capture. Here we see a prepared flyover area of 3.47 square kilometer for a 2018 documentation campaign in Mongolia. In the middle, we see the exported KML file was loaded into Pix4D capture as part of a project, and then a grid flight was embedded on the lower left, with a flight altitude of 100 meter and an overlap of 80%. And on the right at the top, we see the capture strategies possible in Pix4D capture. The exported KML file can be copied to a tablet. After opening Pix4D capture, a new project must be created in order to connect it to a KML file. Now a KML file can be selected in the upper menu area. In the map area, we can change the section directly to the documentation area and start flight planning there. Analogous to the presented recording strategies, Pix4D capture offers comparable missions. For example, the Orthogonal-Grid-Flight can be used as a grid mission with orthogonal camera orientation. To assign one or more missions to a project and to plan them relative to each other, we can add a new mission in the mission area to the right of the map view with the symbol plus. For example, if we select a grid mission, we can place it within the red documentation area, drag it, and add the desired properties. As a practical example, let's look at a flight planning for Orthogonal-Grid-Flight in the Orkhon Valley in Mongolia. In order to be able to fly over as large an area as possible in a short time, the Orthogonal-Grid-Flight with a tight image overlap of 70% is suitable. However, the enormous recording speed also increases the risk of producing a faulty model in the end. This can happen if the weather conditions are not optimal, and for example, wind blows displace some or several camera shots. In the 2018 documentation campaign in the Orkhon Valley, where an area of over 37 square kilometer of the Orkhon Valley was systematically imaged and reconstructed with 2 DJI Phantom 4 multicopters in just under a week, the risk was accepted due to the large area. The objective was to uncover remnants of the urban structure of Karabalgasun and to be able to localize them. This was to complete the existing city model, which was based on a LiDAR survey conducted in 2007. The complete material of the 2018 campaign is available for download on the GeoServer of the German Archaeological Institute. Here we see the analysis of 4 of the numerous flight missions with a total of 913 photos, each capturing an area of 512 times 512 square meters. From left to right, we see the processing of the capture data in reality capture. The resulting ortho image is sufficient for further investigation. However, if we look at the DSM, the bowl-shaped curvature of the model is clearly visible. One reason for this is the tight overlaps and some erroneous camera positions. The upload of the image data took 1 hour, and after 7 hours, the result was ready for download. The ortho image had a ground resolution of 4.05 cm per pixel, and the DSM a correspondingly more coarse with 16.21 cm per pixel. In the DSM, the paths can be seen due to the tightly calculated overlaps. The DSM result was the basis for a detailed investigation of hidden structural features. Let's take a look as a practical example of flight planning in orthogonal double-grid flight in Karabalgas, Mongolia. Let's look at an example of the application of an oriented double-grid flight. In an additional flight of the documentation campaign in the Orkhon Valley in 2018, the citadel of the palace city Karabalgasun was flown automatically. The oriented double-grid flight recording strategy was used for the 3D reconstruction of the citadel. The 775 single-frame images were captured with a DJI Phantom 4 at a flight altitude of 70 meters and processed in reality capture. OrthoImage and DSM each have a ground resolution of 20 cm per pixel. Reality capture is able to reconstruct the captured 775 images into a distortion-free 3D model due to the large image overlaps of 80% and the recurring overlaps of the trajectories. However, remember, the recording time has more than quadrupled here. Let's look at automatic flights in strong winds and especially in the mountains. Automated flying in the mountains is often a difficult matter. The problem is even in good weather, relatively spontaneous and sometimes extreme wind situations. For automated flying, the current wind speed should be measured with an anemometer and taken into account. We follow here the rule. Under normal circumstances, automatic flight can only be performed up to a wind speed of 10 km per hour. Flight planning that is based on single image recordings should therefore only cover a relatively small area. In this way, it can already be observed directly in flight, whether the individual shots can be used sensibly later. The planned single image survey has of course the decisive advantage of the geodata in the photos, which enables an automatic georeferencing of the 3D model. In these situations, manual aerial photography is again a very good alternative or supplement. In this case, the planned single image captures lead to a model in which coordinates can be read out and transferred to the much more detailed 3D model generated by videogrammetry. The level of detail is many times higher, even though a 1080p video recording was used instead of single 12 megapixel images. On top, we see a short automated flight as an oriented double-grid flight at a height of 30 meters centrally above the structure. The resulting 3D model is automatically georeferenced. On bottom, there is a manual flight, and simultaneous video recording can still produce very accurate terrain and structure models in high winds. Let's get back to the flight planning in the software Pix4D Capture. The quality of the alignment and the coverage of the missions depends on the display size of the tablet and the skill of the user. It has been shown that especially for large-scale flights with many recurring missions, the detailed editing of a mission and a subsequent copying and reuse makes the planning much better and faster. When grid size and orientation are set, we can set other mission properties. One of the most important parameters is the flight altitude. We vary the flight altitude relative to the starting point of the mission on the left side of the display and get the theoretical ground resolution in centimeter per pixel in the images if the terrain remains flat in the ideal case. Under settings, we can set other properties such as recording speed, camera orientation, percentage image overlap, and the orientation of the copter. On the left, in the mission planning, the grid can be rotated, scaled, and positioned. On the left part of the application, we can select the constant flight altitude relative to the starting point. And on the right, in the menu, the properties, speed, camera orientation, percentage image, overlap, and orientation of the copter in relation to the flight direction or the grid center. Now let's briefly look at the topic of multi-missions in Pix4D Capture. At first, it sounds fantastic to accommodate all missions in a project plan. In practice, it has been shown that the demand on the tablet's performance in terms of RAM increases significantly with the number of missions. However, this phenomenon only occurs when the missions are processed and saved locally. Therefore, the number of missions within a project should be limited. A project planning with multi-missions should not manage more than 30 flights. Here it is no problem at all to split a project into sub-projects and manage them accordingly. Let's summarize again the main steps for automatic or semi-automatic aerial campaigns. First, we need an analysis of the documentation campaign in terms of location, weather situation, altitude, complexity, effort, legal flight situation, and result of 3D documentation. Second, the establishment of criteria for software evaluation and assessment or selection of current software packages need to be done. Third, sufficient test flights with the planned multicopter in connection with the selected software package are recommended. Fourth, the preparation of the documentation area, for example at Google Earth as KML file, is useful. And fifth, the choice of recording strategies and preparation of flight missions, including flight and recording parameters. Later we will talk about the planning and implementation of documentation campaigns in more detail. After listening carefully to this lecture, answering the following comprehension question should help you to summarize the most important statements again on your own. The practical part is about getting to know the PICS 4D capture software.